Hello, everyone. The topic that I'm going to talk on is emerging trends in learning from sequential data. In machine learning, data is typically featurized in vectors, grids, graphs, or sequences. Most machine learning algorithms use vectors. CNNs or convolutional neural networks use grids. The graphical neural networks use graphs. And recurrent neural networks work with sequences. There are many sequences of data, particularly those measured over time, which is called as the time series data. We come across time series data in many application domains, such as finance, signal processing, that includes audio and video signals, climate, communications, control engineering, so on and so forth. Time series data is particularly important because we can learn trends and make predictions. Traditionally, recurrent neural networks such as long short-term memory, LSTM, have been popularly used for making such predictions. LSTM is probably the most prominent deep learning framework for sequential data in the 20th century. Of late, the invention of the transformer architecture has revolutionized learning from sequential data. There are some even more recent trends which are worth watching that this talk is aimed to introduce. So the agenda for today's talk, we'll briefly cover three major trends in this space. The first is the deep symbolic regression. So deep learning models perform great, but are hardly explainable. Explainability is important for critical applications like in finance, health, and law. Deep symbolic regression is a step towards explainability or the predictions made by the recurrent neural networks. So that's the first topic. The second trend is continuous time neural networks. We all know neural networks have a number of hidden layers. What happens when the number of such hidden layers approach infinity? We get a continuous time neural network. There are many advantages to this approach. In this context, we will briefly talk about neural ordinary differential equations and its variant, liquid time constant networks, often called as liquid artificial intelligence. The third interesting development is mapping data to function spaces. We all know machine learning algorithms map data to vector spaces. What happens if we map the data to a function space instead? There are a few function spaces that are of interest. The one researchers proposed is the function space of Legendra orthogonal polynomials. So we are going to look at that. So that's pretty much what we are going to cover. But let us first look at the deep symbolic regression. Mathematical equations have explained many world phenomena, right? Quite a few of the equations in physics or economics were inferred from the experimental data and observations using human ingenuity and intuition. So for instance, we have several laws in physics. Most of those laws were basically derived by observing data. So can we automate the process using deep learning? So recent research says yes. So this is different from the normal regression because in regression, we assume a mathematical model and fit it to the data, to the given data. In deep symbolic regression, the model expressed in mathematical expressions is evolved from the data. When the data is modeled using mathematical expressions, results inferred from the data have a better explainability. So when you're able to explain numbers with mathematical equations, it's much more convincing. So we look at two approaches briefly on how we can fit mathematical expressions to data. So let us look at predicting a recurrence relation. So this is from a paper, a very recent paper um, by Diascoli and others. So recurrent neural networks are good at predicting what comes next in the time series. But what is the grounds to arrive at that prediction? No one knows. What if the prediction can be expressed as a formula or a mathematical function? For instance, Fibonacci series can be expressed by a formula. Then explaining how the next number is arrived at becomes very easy. Deep symbolic regression does exactly that. It generates a formula for a given sequence of numbers. This particular paper by Diaz-Colley and others uses the now ubiquitously used architecture in deep learning, the transformer. Symbolic regression is nothing new to artificial intelligence. It was previously done using genetic programming. But genetic programming has multiple downsides. It explores a substantially large search space. So that means a lot of computation and hence it is slow. Genetic programming is characterized by randomness and overfitting, and there are some other disadvantages too. So the latest trend is to use deep learning for symbolic regression. So this is a demo put up by Diaz-Colley and team, which I found to be cool. Let us look at it. So we can give a user input. So we could, I would select recurrence prediction so that I can give a bunch of numbers. And my favorite sequence of numbers is the prime numbers. So let me prime numbers list. So I'll just give a few prime numbers like this. And I will ask the model to predict. So this is the user input. Model parameters, I'm not too concerned. I'll just leave it as they are. And yeah, that's it. I just specify the numbers and it tells me an equation, gives me an equation which fits these numbers. So there's an average error of 15.35 because these are prime numbers. It's one of the most difficult sequence to summarize using equations. But still, it does a relatively good job of with an average error of 15%. And if you see the plot, so the prediction is the black line and the prime numbers are the red dots. You can see that it's not too bad, right? The prediction is pretty good. So that is the idea of symbolic regression. So taking a different approach to the same problem, the researchers from Lawrence Livermore National Laboratory use reinforcement learning to train the RNN. The RNN used here is actually the LSTM. So they train this RNN to generate a mathematical formula. This is just an example figure from this paper. So they generate a mathematical formula to the given data. There are other approaches also. Some researchers have used graphical neural networks to do the same, but the idea is somewhat similar. Basically fit a mathematical equation to a given sequence of numbers. So the next topic is continuous time neural networks. Neural networks are known for huge number of parameters corresponding to the huge number of hidden layers of neurons. But surprisingly, as the number of hidden layers tend to infinity, the number of parameters drastically comes down. So let us see what it means to have an infinite number of hidden layers. So we all know artificial neural networks are made of discrete units. The shaded box captures a representation of the input data, right? So this is the input data, and this shaded box captures a representation of that data. So it is made of discrete units distributed in layers. So these are all the discrete units which are distributed in layers. So these are the hidden layers. The hidden layers, basically beat up the input data. So they transform the input data to any shape or form that we need as output. So that's the whole idea of neural networks being universal function approximators. They can approximate any kind of function. For instance, if the input data is animal pictures, the hidden layers could transform the pixel values into probabilities that indicate whether the animal is a lion or a dog or some other animal. So the transformation or the beating up of the numbers happens in the units called neurons. If the connections in the box are recurrent and is a black box of nonlinearities, it is called reservoir computing, but we'll not go there. So each edge connecting these neurons is associated with a weight. So the recent GPT-3 model for natural language processing has 175 billion weights. So that's the kind of parameters that we are talking about. Each weight is a parameter. Another way to look at the whole framework is that the hidden layer is just modeling the input data, basically doing some kind of curve fitting, some kind of regression, right? The black curve is the model of the data. Say, for instance, we are given some data and the model of the data is this black curve. So what are these arrows? These arrows are basically tangents or gradients. So if you look at the Resonant model, right? According to Resonant, by the researchers who published the paper in 2016, this essentially solves an ordinary differential equation. If you recognize this expression, the mathematical expression, it is basically the Euler's method, right? So this is a numerical way of solving this equation. So with an initial condition, an initial condition is given, and we are solving this differential equation using Euler's method. That is exactly what is being done in the ResNet, right? So let us assume that the black curve is the model of the data, and these arrows are the tangents or the gradients that the whole process is computing by numerical evaluation of the differential equation. So think of the hidden layer, HT, as where the previous arrow ends, right? And F as the gradient, right? This is what is happening here. F is the gradient. And so where it stops numerically is where the arrow ends. So that's the gradient. At a microscopic level, every curve is made of infinite small straight lines. So this curve here is made of infinite small straight lines, right? Which are basically tangents. The function computed is not continuous in time, right? This function is discrete. It's numerical way of computing the differential, of solving the differential equation. So it's not continuous in time. So what if we make it continuous? What if we make the time continuous? We'll basically get back the curve. So in the ResNet context, what if we add infinite hidden layers to make these arrows microscopically small? So each of these arrows corresponds to a hidden layer, because remember, ht plus 1 is equal to ht plus this function, which is the derivative. So, what if we add infinite such arrows? Then it becomes continuous, right? So it's as good as solving the continuous differential equation. So that is the whole idea of continuous time neural networks. The hidden state H is now continuous in time, right? We replaced all the hidden layers with this differential equation. We solve the differential equation with respect to the parameters, we are done. So that means there is no need for billions of parameters. There are no longer billions of neurons in the hidden layers. It's all a continuous differential equation that we are going to solve. So there's no need for billions of parameters. Then there's less computational needs. That means it is suitable for edge computing, like on your phone, you can do machine deep learning on your phone using the neural ODE framework. The parameters adapt to evolving data. So, and that is one of the primary advantages of neural ODEs, because it's continuous. So we are better able to adapt to the continuous changing data. And then we can extrapolate to unseen data. That means it can work with choppy signals. So that means there are a lot of applications. So an extension of this framework is the liquid neural networks proposed by the MIT researchers. So it's an improvement over neural ODEs. They introduce a time constant tau. You can refer to the paper for more details. So that way they inherit most of the advantages of neural ODEs, and it is proven to perform better than neural ODEs and other recurrent neural networks. And the next idea that we are going to consider is that of Legendra Memory Unit, basically mapping data to functional spaces. So functional analysis provides us with many tools that are used in machine learning, right? And one of those tools is the notion of a function space. So some leading questions. What is the abstraction for something that can take a finite number of values? So one abstraction is a vector, right? A vector takes a finite number of values. And what is the abstraction for something that can take infinite number of values? So instead of discrete values, we have continuous values. So a variable, right? A variable can take infinite number of values. What is it that can take infinite number of values that obeys certain properties, right? So that is a function, right? So functions are essentially infinite dimensional vectors. A point which has magnitude and direction, which is typically called a vector, is now a function in infinite dimensions. Alternatively, a vector can be seen as a discretized function. So another interpretation of vectors, in addition to single dimension matrix and point with direction, is that of a function. A vector can be interpreted as a function. So we all remember probability mass function and probability distribution density function, right? So this is the mass function is when the probabilities are discrete, and the PDF is when they are continuous. So here's another similar analogy. So a bar chart for a vector of 6 dimensions can be plotted like this. So 1, 2, 3, 4, 5, 6 numbers in this vector. A bar chart of vector with 17 dimensions, 17 numbers, can be plotted like this, 17 bars. A bar chart of a vector with infinite dimensions can be plotted continuously like this, right? So function is basically an infinite dimensional vector. So just like you have a bunch of operators which operate in the vector space, you have a corresponding operator which operate in function space. So the summation becomes continuous, it is integral. Norm is similarly defined. Inner product is also similarly defined. Orthogonality. So all these are defined just like in vector space. The only difference is continuity of the values. So just replace sigma with the integral operation, and you get a lot of the concepts in vector space applicable to function space also. So that's the idea of a function space. Now, what is Legendra Memory Unit? So research. So this is a paper by in NeurIPS in 2018 by Volker and others. So, their research proved that polynomial terms are good to represent dynamics of a system. I mean, not their research, but in general, research proved that polynomial terms are good to represent dynamics of a system. So we have Kalman filters, which is an example of dynamics system, right? So we all know polynomial terms are good at representing them. So mapping input data to vector space is common, but LMU maps it to a function space of Legendre polynomials which are orthogonal to each other. Memory can last for 100,000 time steps. That's what the researchers in this paper claim. The memory, that means the recurrent neural networks are able to understand the dependencies 100,000 time steps before, compared to 100 or more in LSTM, right? Even the transformer architecture, it can go up to 512 tokens back or things like that. Maybe at most 2048. Some researchers are trying to enhance it 2048, but that's it. So it is somewhat similar to reservoir computing, but much more efficient. Scales linearly as compared to quadratic scaling of reservoir computing. So there are actually 8 function spaces that provide orthogonal bases. Fourier transform is something that we all know. We use it for audio signals a lot. But in this framework, we have used Legendre, but there are others also. But the idea is the same. Just like the vectors are orthogonal if the dot product is 0, functions fx and gx are orthogonal in an interval if the integral of the product is 0. So these are all basically sets of orthogonal polynomials. So function spaces provide ways to express other functions in terms of base functions, which are orthogonal to each other. So orthogonal functions provide a way to expand, solve, and interpret solutions to many types of important differential equations. So more details you can click on there. You can search for these. I don't want, because of lack of time, I don't want to spend time on this. But so these are the function orthogonal basis functions which can be used for function spaces. So this is the Legendre. These are the Legendre polynomials which are orthogonal to each other. So these polynomials are obtained by solving a differential equation given above here, right? So when you plot the Legendre polynomials, you get this. So if you have any questions, please feel free to contact me. I am on. I have a website. I'm generally searchable on the internet. I'm on Twitter and other social media. So please feel free to get in touch with me if you have questions. Thank you.